Hi everyone, in this video we will be learning about half subtractor and full subtractor. Under half subtractor and full subtractor we will be looking into combinational design procedure, objective, input and output variables, truth table, Boolean expression, circuit design and finally simulation. Procedure for both half subtractor and full subtractor. Connections are given as per the circuit diagram. Arrange the gates according to the circuit given. Inputs are given using the toggle switch and observe the output and verify the truth table. Objective: to study by designing and construct half and full subtractor circuits and verify the truth tables using logic gates. Theory: half subtractor. The half subtractor is constructed using XOR and AND gate. This half subtractor has two inputs and two outputs. The outputs are difference and borrow. The difference can be applied using XOR gate, borrow output, and can be implemented using an AND gate and an inverter. Nothing but a NOT gate. Full subtractor. The full subtractor is a combination of XOR and OR NOT gates. In a full subtractor, the logic circuit should have three inputs and two outputs. The two half subtractor put together gives a full subtractor. The first half subtractor will be C and A, B. The output will be difference of output of full subtractor. The expression AB assembles the borrow output of the half subtractor. The second term is the inverted difference output of the first XOR. Truth table and circuit for half subtractor. This is the table for half subtractor. You can see here that we have two inputs A and B and two outputs, borrow and difference. This is the circuit for half subtractor wherein we are using one XOR gate, one AND gate and a NOT gate. This inverts the circuit. This is the expression for difference and this is the expression for borrow. By giving 0 at A and 0 at B, we get difference as 0 and borrow as 0. And by giving 0 at A and 1 at B, we get difference as 1 and borrow as 1. This is how we are going to carry on with the K-map. According to the table that we saw previously, we can very well see here that by giving 0 at A and 0 at B, we get difference as 0 and same borrow as 0 as shown here. By giving 1 at A and 0 at B, we get difference as 1 and borrow as 0. Similarly, as shown here. This is how we carry on with deriving expression from K-map for difference and K-map for borrow. The expression for difference here is A bar B plus AB bar and the expression for borrow is A bar B. Truth table and circuit for subtractor. This is the truth table for full subtractor and this is the circuit for full subtractor. We have used two half subtractor circuits for full subtractor. We have used two XOR gates, two AND gates, two NOT gates and one OR gate to connect both the two half subtractor gates. This is the expression for difference and this is the expression for borrow. We have used three inputs here and we have got two outputs. A, B and C are the inputs and difference and borrow are the outputs. K-map for full subtractor. This is the K-map used for full subtractor, from which we are deriving at the expression for difference and borrow respectively. As we saw earlier, by giving 0 at A, 0 at B and 0 at C, we are deriving at 0 for borrow and 0 for difference as shown here. Similarly, by giving 0 at A, 0 at B and 1 at C, we are getting 1 as our difference as shown here. Borrow is 0 but the difference is 1. And that's what is depicted here in the K-map for difference. This is the K-map from which we are deriving at the expression for difference, which is nothing but A bar B bar C plus A bar B C bar plus A B bar C bar plus A B C. This is the K-map for borrow. Here we are using A, B and C as our inputs. By giving 0 at A, 0 at B and 0 at C, we derive at 0 for borrow. By giving 0 at A, 0 at B and 1 at C, we are deriving at 1 for borrow as shown in the table here. Similarly, we are performing the same for other inputs as well. And finally, we are deriving to the expression borrow equal to A bar B plus BC plus A bar C. So this K-map is very well useful in deriving at expression for the circuit. List of components used in this experiment. Half subtractor, XOR gate, AND gate, NOT gate and bulbs are used for half subtractor. For full subtractor, we are using 2 XOR gates, 2 AND gates, 1 NOT gate and 1 OR gate, bulbs. Simulation of half subtractor. In the simulation of half subtractor, we can very well see here that we are using 2 toggle switches, 1 XOR gate, 1 AND gate, 1 NOT gate and 2 bulbs, and we are renaming here it as shown here. Then we are connecting the gates as per the circuit given in the presentation above. Finally, we are checking at the inputs where by giving 1 at A and 0 at B, we are getting difference as 1 and borrow as 0. Then by giving 1 at A and 1 at B, we are getting difference as 0 and borrow as 0. By giving 0 at A and 1 at B, we are getting difference as 1 and borrow as 1. And finally, by giving 0 at A and 0 at B, we are getting as 0 in the difference and 0 in the borrow. This is all about simulation of half subtractor. Next, we are going to look out about simulation of full subtractor. We are using 3 toggle switches, 2 XOR gates, 2 NOT gates, 2 AND gates and 1 OR gate. We are also using 2 bulbs for output. We are naming it as shown here, and finally connecting all the gates according to the circuit given in the presentation. On giving 1 in A and 1 in B, we get difference as 0 and borrow as 0. On giving 1 in A, 0 in B and 0 in borrow in, we get difference as 1 and borrow out as 0. By giving 1 in A, 1 in B and 1 in borrow in, we get the difference and borrow out as 1 respectively. By giving 0 in A, 0 in B and 0 in borrow C, we get difference as 0 and borrow out as 0. And this is how we proceed with the simulation of full subtractor. Finally, the result is nothing but combinational circuit for subtractor is being designed and implemented and the output is verified. This is all about half subtractor and full subtractor. In the next video, we will be looking about the code conversion of binary to gray and gray to binary. Thanks for watching.